Today's lesson, we're looking at binomial probability distributions. We're still investigating distributions in general. This is the second type that we're going to investigate in this 4-lesson unit. And binomial probability distributions are a little bit different than what we talked about before.
Yeah, we looked at uniform distributions where the outcome of each possible event is the same probability as all the other ones, like the number on a face-up die.
And that's a little boring.
And it gets a little more exciting too.
Yeah, and it doesn't model everything that we'd like it to model. So we need to expand on that discussion a little bit.
Yeah.
So what's a binomial distribution?
All right, so to think about what a binomial distribution is, we're first going to look at what a binomial experiment is, because the distribution is going to be all the possible outcomes of the experiment. And a binomial experiment is one that possesses these 3 properties. First of all, it consists of a certain number, n, of repeated trials. So, so you're going to do something over and over again. And these trials, they're given a particular name. They're called Bernoulli trials after Jacob Bernoulli. But to be a Bernoulli trial, it has to be independent, so the probabilities are independent, random, so it's due to chance and not skill or some other factors, and there have to be only 2 outcomes, a desirable outcome and everything else. So hence the word binomial, right? So this leads into part 2. I've sort of summarized what a Bernoulli trial is there in three small parts, but the rest of it, each trial results in an outcome that can be classified as a success or a failure. If you needed to roll a 6 to get out of home on a board game, then 6 would be success, everything else would be failure. So you can see how the probability of success is 1 in 6, and the probability of failure is 5 out of 6. So these 2 options that you have, I mean, sure, you could get a 2, a 3, or 4, or 5, or a 1, but those are all lumped into one category as failure. And because the name binomial implies, like one of 2 possibilities, that's what we're looking at, success and failure. The probability of success we denote by a lowercase p, and that has to remain constant from one trial to the next. So the idea here is that you'd have to be replacing the cards, or you'd have to be replacing things, or it would have to be...
Because they have to be independent.
Independent. So as long as the trials are independent, there's 2 options, success and everything else, okay? And it's random, so that there's no possibility for any kind of skill. Then we've hit a binomial experiment. So then we can come up with a binomial distribution.
All right, so again, the number of successes x in n trials of a binomial experiment. This would be known as a binomial random variable. Okay, so here is the formula that we're going to use for our binomial distributions, and that's that the probability of any outcome is equal to n choose x, p to the power of x times q to the power of n minus x. We need to look at what these things are. Okay, n is of course the number of trials, and x can be 0, 1, 2, 3, 4, all the way up to n.
And x is the number of successes.
Yes.
So if you want the probability of 3 successes, then x would equal 3. If you want the probability of no successes, so all failures, then x would equal 0.
And in a distribution where we're looking at every single possible different outcome, then x would take on all of these values.
Yeah.
P is the probability of success in a single trial. Q is the probability of failure in a single trial. So you're going to want to note this right here. This is, of course, just finding the complement.
Complement, yeah,
right?
Because you either have success or not success. Yeah, like, those are your only 2 options.
And n choose x is, of course, a combination.
Yeah.
And so we'll see that more and more often.
Because if you had n items in a line, and say you've got 5 trials, and you want the probability of 3 successes, well, those 3 could come like the first 3, or could be 1, 2, and 4, or could be 2, 4, and 5. So we're taking a combination just because we know that to have 3 successes, there are multiple ways of choosing 3 out of 5, and so we have to incorporate that value into our calculations.
Yeah. So what kinds of things is this going to work on? And I think that's probably one of the biggest questions that students have. Okay, where am I going to use it? And so the rest of this lesson really is devoted, to kind of showing, okay, this is exactly where you're going to use these. So by the end of, I don't know how many examples we have, 4 or 5, but at the end of this, you should probably see, okay, that's where I'm going to be using this type of distribution.
Yeah.
So here's an example. Example number one. A die is tossed 3 times. What's the probability of A, no 5s turning up at all, of 1 5 turning up, or of 3 5s turning up? So already now in contrast to what we did in unit number 3, which was just basic probability, already we're solving more sophisticated probability problems because we're looking at tossing a dice 3 times and finding the probability of certain outcomes within those 3 tosses of the dice.
Yeah.
Okay. So we're going to skip part A first. We're going to come back to it in a minute. But what's the probability of 1 5?
Okay.
So what we have to say is, okay, so we're tossing a dice
3 times.
3 times.
So that's 3 trials in a probability experiment. So we know that n equals 3. Okay.
Yep.
So part of the skill here that you're going to develop is in dissecting the problem and then interpreting it so that you can assign values to your variables that are in the formula.
So if I'm looking at 1 5, that's telling me a little bit of information.
Yeah.
Again, because this is a dice, the probability in any individual trial of getting a 5 is 1 in 6.
Yeah. And since we're counting 5s, like since we're saying, all right, I want 1 5, I want 3 5s, I want no 5s, then getting a 5 is a success.
That's a success. That's what we're interested in.
Yeah.
So
everything
P
else
is equal to 1 6. And everything
failure.
else then, getting a 1, a 2, a 3, a 4, or a 6 is a failure. And there are, of course, 5 options for that.
Yeah.
So Q is 5 over 6. Yeah. Okay. Here then, we would say, okay, in this specific example, I want the probability of only 1 5.
1 success out of 3 trials.
And so what that tells us is that X then is equal to 1.
Yeah.
Okay.
Okay, so now let's figure out what we're going to use in our formula. Oh, there it is.
There it is.
Oh, it's on fire.
So
all right.
there's the binomial formula, and it's up there so that we can kind of refresh our memory and say, all right, now what we need is to fill in this in the appropriate way. So first of all, we're talking about the probability of 1 5. So P1.
Yep.
Right? The probability of 1 5.
1 success.
Right? So we know that n is equal to 3 because we're throwing the dice 3 times. So 3 choose 1. Right? So it's basically the success. So only 1 5. That's what we're looking at.
Yep.
P to the power of x. So it's 1 6 to the power of 1. And 5 over 6 to the power of 2.
Yep.
Because 3 minus 1 is, of course, 2.
Yeah.
When we complete this calculation, 3 choose 1 is 3. A 6 to the power of 1 is a sixth. And 5 6 to the power of 2 is 25 over 36. And when we multiply this out, we get 75 over 216, which is about 34.7%. So what this has just told us is, hey, if you're tossing a dice 3 times, what is the probability of 1 5? Well, it's a 34.7% chance.
Yeah. And note, there's a very clear pattern to the way this works. You've got 3 trials, and you only want one of them to be a success. So there's your n choose x. So now here's the probability of success, and there's that 1 success that you're looking for. Well, if you're only having 1 success out of 3 trials, then the other 2 are failures. So notice that your P and Q should add to 1 because you only have those options, success and failure. And that the exponent on P and the exponent on Q should add to n because if you only have 1 success, the other 2 trials have to be failure. Okay? So note, like those are simple things that just make sense. Once you've done a lot of these, notice your P and Q have to add to 1. Notice your 2 exponents have to add to n. And you're just finding how many ways can I choose one thing to be successful if you want the probability of 1 success.
Okay, so let's say we do the miraculous. Let's say we throw the dice 3 times.
Yep.
And we want to find the probability. We've just rolled 3 5s in 3 trials. What's the probability of that? Well, we still know that P is 1 6.
Yep.
We also still know that Q is 5 over 6. These things don't change.
They're changing, yep.
Okay. X, however, now, because we know that n is equal to 3 because it's 3 trials. Here, x was equal to 1 because we cared about 1 5. Here we're saying, hey, we want 3 successes in 3 trials. So x is equal to 3. Well, here the probability of 3 5s is 3 choose 3 times 1 6 to the power of 3 and 5 over 6 to the power of 0.
Because we want 3 successes and no failures.
Exactly.
Right? So the exponent on the failures is 0.
And this is exactly 1 in 216. So this isn't even half of a percent probability. This is a very, very small probability.
Is that why Yahtzee is so hard, Mr. Johnson?
It is. That's why in one roll of 5 dice to toss 5 of the exact same number, the probability that, if you can imagine adding, expanding this and how tiny that probability would be. To roll 5 dice and get 5 of the same number, it's a very, very, very low probability. Okay, so now let's look at no 5s turning up. We did 1 5 and 3 5s because it's a little bit easier to see what x is. When we have no 5s turning up, x is equal to
0. No
0.
successes.
Yeah,
we want no successes, all failures.
Yeah. So the probability of this, and of course, it's interesting. It'll be interesting to compare the result of A to the result of C. What's a higher probability? Rolling 3 dice is it a higher probability that you'd get no 5s, or is it a higher probability that you get all 3 5s? Right? So we can say P0 is equal to 3 choose 0 times 1 over 6 to the power of 0, 5 over 6 to the power of 3. And when we multiply this out, we get 125 over 216. And indeed, 57.9% of the time, this is what's going to happen, right?
You won't get any 5s.
So you're not going to get any 5s.
All failure.
Almost 58% of the time.
Yeah.
Right? So if you can see, and you think about this in the context of a game, at say the games fair for your final culminating task, you know, this would be a game, you know, that you could play that's very similar to Yahtzee, and basically you just call it, you know, and you could assign monetary values to each of these situations. So let's take a look at what the expected value is.
Okay. And let's note that in 3 trials, we've already investigated the probability of getting no 5s, 1 5, and then all 3 5s. So in terms of all the possible outcomes, we're just missing one of the outcomes. We're just missing the probability of getting 2 5s. And so if we want to create a distribution for this experiment, then we want to set out the values for x and then find the probability for each value. We've already done the probability of 0 successes, the probability of 1 success, and the probability of 3 successes. Now we can pause right now and you can calculate P of 2 equals 3 choose 2 times 1 6 to the 2 times 5 6 to the 1. But we can also capitalize on what we know about probability distributions, that they should sum up to 1. So if you take 216 and you subtract 125, you subtract 75, and you subtract 1, you'll be left with 15. And so we know that if we were to add up those 4 probabilities, we would get a sum of 1. So we've just completed the distribution because we've already done most of the work there anyway. Those are all the possible probabilities for all the possible outcomes for this experiment. And now let's say, okay, well, you know, what is the expected number of 5s that you could get? I mean, we've seen it's a very high probability of getting no 5s. Kind of like a medium probability of getting 1 5, really low probability of getting 3 5s. Like, how many 5s could you actually expect if you rolled a die 3 times?
And when we add these up, we get 108 out of 216, which is 1/2.
Oh, so I could expect to get a half of 5 in 3 rolls.
And can you get a half of a 5 in 3 rolls?
No.
So we need to interpret what this means. The mathematics is telling us that the expected value for this game is 1/2. What we need to say then at this point is we need to say, what does that mean?
Kind of means that it's either going to go back and forth between getting no 5s or getting exactly 1 5 if you're going to roll it 3 times. If you were to do this over and over and over again for infinity and then average it all out, the number of 5s you'd get on 3 rolls would be 0.5. You know, it's going to go back and forth. And that's because it would be 1 out of 6. So when you shake that down as a proportion, half out of 3 is the way that we can make sense of it. So we could expect between 0 or 1 5 on average if we did this. As a class, if we did this, we'd have the majority of people getting no 5s or 1 5.
Yeah, and then when we averaged people, everyone's results,
we'd get about
we'd say,
0.5.
oh yeah, there's 0.5. The answer is 0. We get basically an average of 0.5.
That's what we'd expect.
All right. So expected values, though, just like we've just calculated, can there's actually a little bit of a workaround.
Yes,
expected
that's
values.
only good for it doesn't
Yeah.
work for the uniform distribution.
No.
The uniform distribution, you have to make the full table of distribution values
Yeah.
and then do the product and the sum.
Yeah.
But you're right, there's a workaround.
Here,
for the
there's a
binomial.
workaround in the binomial distribution. And because the probability of success for each trial is the same, the expectation value for a binomial distribution is the probability of success for each trial times the number of trials.
Yeah.
Okay.
So remember, our probability of success was 1/6, and our number of trials was 3. So 3 times a sixth was 3/6, which was our half, just like we got.
There it is.
Yeah.
So hospital records show that patients suffering from a certain disease, 75% of them are going to die as a result of it. Okay, so it's a particular disease that's in a hospital, and 75% of patients are dying from it. What is the probability that of 6 randomly selected patients, 4 will recover? Right, so if 75% of patients are dying as a result of this disease, let's say we go around and we select 6 of these random patients that all have the disease, what's the probability that 4 of them are going to get better?
It should be low, right? Because 4 out of 6 is a pretty high number considering 75% die as a result. But we can look at this and we can say, all right, well, it's independent. Like if one person dies or survives, it's not going to affect whether the next person dies or survives. So we know they're independent. We've been given, a rule, and the rule is 75% die as a result. This is on average. So that's our probability, of success or failure, depending on how you want. We're going to call dying a failure probably. And what is the probability that of 6 selected patients, 4 will recover? Those 6 people that we selected, well, that's our experiment. And 6 people, like if we're going to do it 6 times, then 6 is the number in our trial, right?
Exactly. So, dying is a failure. It's an epic failure.
Let's say we're going to consider that to be our Q value.
All right. So, and recovery is, of course, a success. So here we'll say P is equal to 0.25 and Q is equal to 0.75.
Yeah.
Okay. So we've already talked that N, we're randomly selecting 6 patients. So we have 6 trials, really. And of course, the number that we're interested in, the number of successes that we're interested in ascertaining is 4.
Yep.
Okay. So basically, the probability that 4 recover is 6 choose 4 times 0.25 to the power of 4 times 0.75 to the power of 2.
Yeah.
And when we calculate this out, we get 135 and 4,096.
Notice that to do the calculation, we did convert 0.25 to 1 over 4 and 0.75 3 over 4. Fractions are often easier to use and can be more precise and require a little less rounding. So you can use your judgment there.
So this is 0.033. So we would say that basically the probability that with this disease that 4 out of these 6 randomly selected patients will recover is only about 3.3%.
Yeah.
And that's a little daunting. What's the expected number?
To recover.
Yeah.
Okay.
So what's our expectation value for recovery? Like how many, realistically on average, how many of these 6 patients, randomly selected 6 patients, how many
should recover? Well, this is because it's a binomial distribution. We can use the go around for our expectation. We don't have to calculate all of the different outcomes and then average them. We can just take the number of trials times the probability of success. And again, we defined success as recovery. So the number of trials was 6, and the probability of success was 0.2525%. So you'd expect 1.5 people out of those 6 people to recover. So if you wanted to make sense of that for a layperson to understand, then you could say, you'd expect between 1 and 2 people to, every time you took a sample of 6 people suffering from this disease, you'd expect 1 or 2 of them
would recover
to survive and recover. Yeah.
Okay. All right. In the old days, and we're talking old days.
Like when phones were first invented. Yeah.
There was a probability of 0.8 of success in any attempt to make a telephone call.
So 20% of your calls will go to the wrong people.
Yes.
Imagine if 20% of your text messages
went to the
wrong people.
It could spell disaster.
Yeah.
Calculate the probability of having 7 successes in 10 attempts. So Maud is sitting at her telephone and she's about to make a phone call. And she wants to figure out, okay, what's the probability of 7 successes in 10 attempts? Okay. Well, what we can say here is, all right, well, 10 attempts, that's telling us something.
That's the number of trials. We're going to do this 10 times over and over again.
The question actually tells us that the probability of success is 0.8.
Great. So the probability of failure is just 1 minus 0.8.
Yeah, exactly.
Yeah.
N is, of course, equal to 10. And because we're interested in the probability of 7 successes, x is going to be 7.
True.
All right, so when we put this together, the probability of 7 successes, 10 choose 7. Probability of success to the power of 7. Probability of failure to the power of 3.
There we go.
0.201, so about a 20% chance. The probability of 7 successful attempts in 8 tries is about 20%.
Oh my gosh, fantastic.
All right, bow and arrows. A blindfolded marksman.
Because it's more interesting if the marksman is blindfolded.
Of course, it always is.
Yeah.
A blindfolded marksman finds on average he hits the target 4 to 5 times.
That's pretty good.
If he fires 4 shots, what's the probability of more than 2 hits, at least 3 misses?
All right, at this moment, you should be crying into your notebook a little bit, because as soon as you see more than or at least you know thinking, you're doing cases.
Oh boy.
And so it's not exactly 2 hits or exactly 3 misses. We're looking for more than 2 hits or at least 3 misses. And so now we need to sort of figure out, okay, are we counting hits or are we counting misses? Because generally, if you want to figure out what your p-value is,
yeah, you need
whatever
to figure
it is
out,
that you're counting,
okay, what's a success?
Is your success, right?
And so I guess in this case, it kind of makes sense to talk about, a hit being a success, right? So if he hits the target 4 out of 5 times, we'll say he's successful 4 out of 5 times. So P is 4 in 5.
Yeah.
Then failure, Q, is 1 in 5. The probability of failure in any one trial is 1 in 5. So he's firing 4 shots. So basically he's taking 4 trials. So N is equal to 4. And we're looking for an X value that's more than 2. So we're looking for either 3 or 4 hits out of 4 shots.
Yep.
Okay. So again, this is going to be a case. So case 1, we're looking at 3 hits.
Yep. 3 successes.
Case 2, 4 hits.
Yep.
All right. So here's the probability of 3 hits. 4 choose 3 times the probability of success to the power of 3 times the probability of failure to the power of 1. 4 times 0.512 times 0.2, and of course the probability of success in this case is 0.4096, so about 41%. Yeah. In the case of 4 hits or 4 successes,
all 4 success,
yeah, so we'll get 4 choose 4, and then the probability of success to the power of 4, and the probability of failure to the power of 0.
That's right.
And of course this, if we multiply it out, is of course something very similar to 0.4096. So we add these two things together. The probability of more than 2 hits
is the probability of 3 hits plus the probability of 4 hits. Because we wrote it right there. If it's got to be more than 2, then it can be 3 or 4. And there is your or right there.
So we got 81.92% as the probability. That's pretty good for a blindfolded marksman.
You got it.
All right, now let's flip it all around. Or do we have to flip it all around?
Well, we don't have to flip around. We just have to flip around our thinking.
Okay.
If he's going to miss at least 3 times, then he needs to have 3 misses or 4 misses, right?
Yep.
If you have 3 misses, then he's succeeded once. If he's had 4 misses, then he's succeeded 0 times. So by working backwards in terms of how many failures or how many misses, then we've determined actually that the X values here then are 1 and 0. Okay, so 1 success or no successes if we want 3 failures or 4 failures. So we're going to keep everything else the same. We're going to keep our P's and Q's the same. We're going to keep everything else. And now we're just going to find the probability of 1 or the probability of no successes.
Yeah. And we're going to do it in a shorthand way here because we know that these two things are going to be added together. We know that this represents a case and that this represents a case, and that's fine. So we'll just write them right beside each other. We got 4 choose 1, and then we got the term with 4 choose 0, and we can figure out this is 16 in 625 plus 1 in 625. And you'll notice, sometimes we are flipping back and forth, and it's basically whatever you're most comfortable with in your calculator.
Yeah.
Right? Sometimes this requires rounding, whereas a fraction wouldn't require rounding.
Yep. Fractions are very precise.
Because this would be 17 in 625, right? Because this is what the probability is going to be. And that's about 2.72%.
Sure.
So there's much actually better possibility of
that he's going to get them than he's going to miss them.
Yeah, exactly.
Exactly.
Okay. So a manufacturer of metal pistons finds that on average 12% of his pistons are rejected because either oversized or undersized.
And notice here that you've probably read this a few times. On average, he makes 4 to 5 shots. On average, 12% are rejected. This on average is your indication that this is like an independent probability. Because this has been calculated, already calculated,
Yeah.
and this has been given
Yeah.
to you. There are times where we might say to you, in a bag of marbles, 4 out of the 15 are red. And that's different. We're not saying on average bags of marbles have 4
No.
And so be careful with this. As soon as you see this on average,
Yeah.
then you're good. This is an independent probability,
Yeah.
12%, and you can use that in your binomial distribution.
So if 12% are rejected,
Mm-hmm.
what's the probability that a batch of 10 will contain no more than 2 rejects?
Or at least 2 rejects.
Exactly.
So here's the thing, and this is where, we define success and failure, but oftentimes you will see binomial distributions defined as an answer to a yes or no question. And so whatever it is that we're counting, if I'm counting rejects, and I'm like, wait for it, there's one, put a check mark on my tally. Wait, oh, there's another reject, check mark on my tally. Then whatever it is I'm counting, whatever it is I'm interested in or looking to tally, I'm considering that a success because it's going to put a check mark on my page. So even though the notion of a reject being a success seems a little weird, if we're counting rejects and we're waiting for rejects, and rejects are the things we're checking off on our list.
That's a success, right? If you're paid to find rejects, then that's a success. You've been successful. You found one. So although rejecting a piston may seem like a failure, and certainly it would be to the manufacturer, here in this case, we're going to consider a reject as being a success. Okay. So this question is a try this question. Okay. The answer for part A is 89%, and the answer for part B is 34%. And so go ahead and press pause. Use example number 4 as a template for how you might think about solving this, and we're going to present the solution now. So presumably you've kind of worked this out, and if you got stumped, here's the answer. Well, the probability of success in this case, which is the probability that something's rejected, is 0.12. The probability of failure, which is that it's not rejected, is 0.88.
And we're doing a batch of 10, so n will be
10 trials.
So
this is the next step. If you got this together, awesome. You can give yourself a pat on the back because you found this. Now we need to interpret what this means right here. No more than 2 rejects. All right. Well, what it means is no more than this means that no rejects, 1 reject, or 2 rejects
are desirable.
Are the desirable cases. So when we do the binomial distribution for 0, 1, and 2 in this case, and we add them up, we of course get 89.2. Okay. At least 2 rejects. Again, the same thing. P is equal to 0.12, Q is equal to 0.88, N is equal to 10. So the same things here. At least 2 rejects. So
we want 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. So there's a lot of desirable cases.
Could I use something else?
Yes, because there are only 2 undesirable cases, 0 and 1. So if we do 1 minus probability of 0 minus probability of 1.
It's like an indirect method.
It's just an indirect method. And it's just that there's too many desirable outcomes and just only a couple of undesirable outcomes. So we'll just use complements in that sense.
And we've even already worked out these probabilities. We worked them out right up here.
That's great.
And so if we do this and we subtract, we get 34.1%.